Hello, good people. Welcome to the next video here. I'm going to bypass example 5 so that we can look at some implicit differentiation problems. And this is going to take us back to, oh, was it two units ago? Definitely 2 months ago for sure, of trying to find the derivative of an equation that is not solved for y. So example 6 could be straight out of an AP free response question here. Consider the curve defined by this equation. Show that dy dx is equal to this formula. So I need to find the derivative and show that the derivative actually equals 3y minus 2x divided by 8y minus 3x. That's what we need to do. Okay, so how do we find the derivative? Well, remember, we find the derivative since we're looking for dy dx. I got to find the derivative, d dx, of the first term plus d dx, the derivative of the second term, and set it equal to the derivative of the first term on the right side. That would be a 7, plus the derivative of the second term on the right side. So why do I put the d dx? To remind me that whenever I'm taking the derivative of a term that's in terms of x, that's just a regular derivative, right? Just a normal derivative. But when I'm taking the derivative with respect to x of a term that doesn't have an x, then I have to treat this variable as a function of x, and therefore I have to do a chain rule. So just as a recap, this is what it would look like. Take the derivative of x squared, so that would be 2x. However, take the derivative of 4y squared, that's 8y times dy dx. I have to multiply by the derivative of the inside, and I'm kind of seeing this function as an inside function, so I got to find the derivative of y, which would be dy dx. I'm going to set that equal to the derivative of 7, which is 0, plus the derivative with respect to x of 3xy. Well, now I have a combination of functions. I have that times that. So I need to do a product rule. And to do the product rule, I'm going to take the derivative of the first. Let me just use purple here. Take the derivative of the first times the second, plus take the derivative of the second times the first. So I have to take the derivative using the product rule. Okay, so I took the derivatives. Awesome. I'm going to put anything that has a dy dx on the left side of the equal sign, and anything that doesn't have a dy dx, I'm going to move it to the right side of the equal sign. So 8y dx is already there, but I'm going to subtract this to the other side of the equal sign and set it equal to 3y is already there, but I'm going to subtract this to the other side of the equal sign. And now I have everything with the dy dx on one side, anything that doesn't have a dy dx on the other side. Next step, factor out a dy dx. If I do, that's going to leave me with 8y minus 3x. And if I divide both sides by the parentheses, the parenthetical expression here, then dy dx is 3y minus 2x divided by 8y minus 3x. Did I show what I needed to show? I did. I can see that this is the same as this. It has been the case that in some years, there is a free response question that has something like letter A. And if you just do the derivative using implicit differentiation and show that it equals what they want you to equal, what they want for it to equal, then you're done. All right, let's keep going. Show that there is a point P with an x-coordinate of 3 at which the line tangent to the curve at P is horizontal. Okay, show that there is a point P with an x-coordinate of 3 where the line tangent to the curve is horizontal. So let's write down what they want. Tangent line horizontal means that dy dx is equal to 0. So I need to figure out where this derivative is equal to 0. However, the derivative is equal to 0 whenever the numerator is equal to 0. So therefore, 3y minus 2x, I need to set to 0. But they said show that there is a point with an x coordinate of 3. So if I substitute a 3 into here, into my formula, am I going to get what I want? Well, that would mean that this would be 3y minus 6 equals 0, 3y is equal to 6, and y is equal to 2. So the question is this the point? Because this x and this y, when I put them into the formula, into this formula, will produce a 0 fractional answer, and that would mean that the derivative is equal to 0, and I have a tangent line. But is this point even in the original function? So I have to check, is this x and y coordinate going to make the original function, I shouldn't say function, the original equation true? And so we start by saying, okay, well, let's go back over here and let's start substituting values that we know or that we think we know. If x is 3, then 3 squared plus 4 if y is 2, 2 squared. Does that equal, I'm going to put a question mark because I don't know if it equals, 7 plus 3 times 3 times 2. So I'm taking this x and a y that I know makes the derivative equal to 0, and I know that because if you want to check it, that equals 0 over 7, which is 0. So that checks out. But is this even a point? Is this x and y coordinate even a point on the original curve? That's what we're checking over here. Well, that would be 9 plus 2 squared is 4. 4 times 4 is 16. And together that's 25. So the question is, does this side equal 25? And this would be 7 plus 3 times 3 is 9. 9 times 2 is 18. And 17 plus 18 is 25. So yes, there is a point that this x and y coordinate, so there is a point P at 3 comma 2 at which the tangent line is horizontal. How do I know that? Because this x and y pair made the derivative equal to 0, and this x and y pair is actually on the curve, which I guess I should check first, right, to make sure the point even exists. Does it make it, does it satisfy, I guess, that, that condition? All right, next one. Find the value of the second derivative of y with respect to x at the point P in part B. Does the curve have a local maximum or a local minimum, or neither at point P? Well, how do I find the second derivative? How do I find the second derivative? Oh, by taking the derivative of the derivative, right? If I can take the derivative of the derivative, then I'm good. All right, so then that means the second derivative of y with respect to x is equal to the derivative of the derivative. So I'm going to take the derivative. I'm going to write down what I need, right? I'm going to take the derivative of the top, the numerator, times the bottom, the denominator, minus the derivative of the bottom. I'm going to zoom in here in a little bit, times the numerator, the top, all over the bottom squared. So here's a good example of once I take the derivative, I really don't need to simplify. Since I have a point that I can check, I'm just going to plug it in and check. So let's start taking the derivative. The derivative of 3y would be 3 dy dx minus the derivative of 2x would be 2. So that's this part. times 8y minus 3x, that's still there, minus the derivative of 8y would be 8 dy dx minus 3 times 3y minus 2x all over 8y minus 3x squared. At this point, I've taken all my derivatives. Notice that I have a dy dx. That means I need to figure out the derivative at this point there. But what was special about this point and its derivative? What happened when I plugged in this x and y value into dy dx formula? What did I get? Oh, I got 0. So that means wherever I see a dy dx, I can replace that with 0 because I know that the first derivative at this point is equal to 0. So wherever I see a dy dx, that would be the first derivative. The derivative is equal to 0 at that place. Okay, I'm not going to simplify. What I'm going to do is I'm going to start plugging in this x value and this y value in this formula. In the first set of parentheses, that's going to collapse down to negative 2. In the second set of parentheses, it's going to be 8 times 2 minus 3 times 3, right? And then minus. This is going to collapse to 0, so 0 minus 3 is just negative 3 times 3 times the y coordinate minus 2 times the x coordinate. Let me make it a little bit clearer. All divided by 8 times the y coordinate minus 3 times the x coordinate squared. So far, so good. What do we notice about this? What is 3 times 3 minus 2 times 3? The whole thing becomes 0. And 0 times negative 3 means this whole thing is going to be gone. And when I come over here, my leftover here, this is the same thing as this, except the denominator is squared. So I can cancel and reduce, I should say, this set of parentheses with one of the two sets of parentheses that's down here, and I'm left with negative 2 over, I'm going to go ahead and multiply this, 16 minus 9. And that's going to leave me, I think I did that correctly. Yes. That'll be negative 2/7. So I cancel this whole thing. Maybe I should do that in a different color. I reduce this whole thing with one of these, and I was left with one on the denominator. And I went ahead and multiplied this out. 2 times 8, 3 times 3, and 16 minus 9 is 7. What did we just find? This was the second derivative. The second derivative is less than 0. If the second derivative is less than 0, that means it's concave down. If it's concave down, and this is a critical point, I know that because the first derivative is equal to 0, that must mean there's a relative or local maximum. So here's where we answer. Since dy dx at the point 32 equals 0, and d2y over dx squared at the point 32 is less than 0, in other words, the second derivative is negative, it's concave down, by the second derivative test, there is a local maximum at the point 23. Does that make sense? We're using the information that we were using in the first videos, but in this context, it might not seem we could use it, but we can, because in part B, we showed that there's a point where the tangent line is horizontal. That means the derivative is equal to 0. And in part C, I showed that the second derivative is negative. So if the first derivative is 0 and the second derivative is negative, that means there has to be a local maximum according to the second derivative test. That was a bear of a problem, and this is the last video that we're going to do for this section. We'll come back in class, we'll practice the rest of the videos, the rest of the problems, and go from there.